With this video, we're going to look at second law problems and how to solve them. When we draw a free body diagram and we identify the different forces acting on the object, for example, here we have a tension force on a string of 1200 newtons and a gravitational force of 8 newtons. Second law tells us that the net force is equal to mass times acceleration. Now, mass and acceleration are things that you can put on a scale, or you can identify using velocities, and that information may be given in a problem. But to find our net force, we have to look at the two forces that are causing the acceleration, and they have to be unbalanced. So when I look here, tension's 1200 and gravity's 800. Tension's going upward, gravity's going downward. So our net force is force of tension minus the force of gravity, or 1200 minus 800. So our net force is 400 newtons. Here, air resistance of 600 newtons, gravitational pull of 800. Our object's accelerating downward because the downward force is greater. That's the unbalanced force. So to find our net force, it's still the positive force, force air, minus force of gravity. 600 minus 800 for a net force of negative 200 newtons. And since force is a vector, we know it's going downward, hence gravity winning. A lot of things we look at will be on a horizontal surface where normal force and gravity are equal. Remember, the force of gravity is equal to the mass of the object times acceleration due to gravity, which is 9.8 on Earth. Here we have friction with no applied force. So our unbalanced force is running horizontally. Our vertical forces are balanced, which means normal force and gravity are equal. Frictional force is going one direction, but we have no other force here. Since it's going to the left, we say our net force, in this case, is just negative 20. So draw a free body diagram, identify net force from the information that is provided. A few things about misconceptions that could occur. Now, we're not going to talk about things going at a slope for everybody, but think about A versus B versus C, okay, for the form of sledding down a hill. At A, we're going to accelerate as we go down the hill. We're going to have gravity and normal force. Gravity and normal force in a horizontal sense, like we see here, are going to be equal to each other. But as we go down the slope, it won't be. But everything we deal with initially is going to be on a flat surface, either flat on the horizontal or straight up and down in the vertical, so that we don't have to worry so much about slopes and angles. But when we're in a flat surface, understand normal force and gravity are equal, because the pull down of gravity is being counteracted by the push up of, in this case, the sled on the body as opposed to the ground, but essentially it's still a normal force. So here's your first example. We have an applied force of 50 newtons is used to accelerate an object of mass 10 kilograms to the right across a frictional surface. The object encounters 10 newtons of friction. Determine the acceleration. First step, free body diagram. What forces we got? Well, we always have gravity. And it's on a flat surface, or we assume so. It's going to be normal force. We know normal force is equal to force gravity, which is equal to mass times g. Our mass is 10. G is 9.8. So normal force and the force of gravity is both 98 newtons. Now we have an applied force going to the right, we'll say. And then we have friction, which always opposes motion. Force applied is 50 newtons. Force of friction is 10 newtons. Newton's second law says net force is equal to mass times acceleration. Our net force is applied force because it's going to the right, minus our frictional force because it's going to the left, is equal to our mass of 10 kilograms. And we're going to solve for A. Applied force is 50, frictional force is 10. 10A, 50 minus 10 is 40. 10A, we divide 10 by both sides. A is going to be 4 meters per second squared. So that's our acceleration there. Another example, Kate and Rob are using a hanging mass in a pulley system to exert 2.45 newtons of rightward force on a half a kilogram cart to accelerate it across a low friction track. If the total resistance to the motion is 0.72 newtons, what is the cart's acceleration? Very similar problem, just worded differently. Here's our cart, our free body diagram. There's gravity. Since it's being accelerating across a low friction track, we can assume that this is going to be a horizontal acceleration. Therefore, normal force equal to the force of gravity equal to mass times g. Our mass is 0.5 kilograms, and we're multiplying that by 9.8. So our normal force and our force of gravity are both 4.9 newtons. We have an accelerated force and a frictional force. Alright, so on our applied force and our frictional force, we know that force net is equal to mass times acceleration. Our force net is going to be our applied force minus our frictional force equals m times a. Our applied force is 2.45 newtons. Our frictional force, or our resistance force, is 0.72 newtons. And that's equal to our mass, 0.5, times our acceleration. So 2.45 minus 0.72 gives us 1.73 newtons, equal to 0.5a. Divide both sides by 0.5 to find our acceleration, and our acceleration turns out to be 3.46 meters per second squared. Now we're going to try to determine all forces. So we got a rightward force applying a 6 kilogram object to move it across a rough surface at constant velocity. The object encounters 15 newtons of frictional force. So we want to find gravitational force, normal force, net force, and applied force. They all start the same way. We draw a free body diagram. Again, we're moving it across rightward, so we know gravity and normal force are going to be equal. So normal force equals gravitational force equals mass times g. Our mass is 6 kilograms, and g is 9.8. 6 times 9.8, and I'm just going to round this to the 10th, 58.8 newtons. So gravitational force and normal force, we know, 58.8 newtons. Our net force and applied force. So we have our force applied, and we have our frictional force. Our frictional force is 15 newtons. Net force equals mass times acceleration. Force applied minus force of friction equals ma. Our force applied we don't know. Our force of friction is 15 newtons. Our mass is 6 kilograms. Now what is our acceleration? Well, we read the problem again and we see this right here. Constant velocity. If we have a constant velocity, that means our acceleration is 0. So 6 times 0, which is 0. So force applied minus 15 equals 0, which means our force applied, if we add 15 to each side, is now 15 newtons. Net force is 0 because mass times acceleration is 0. And then our applied force is 15 because our frictional force is 15. Look for that sometimes. And then lastly, we have a 34.5 Newton rightward force on a 4.52 kilogram cart accelerated across a horizontal surface at a rate of 1.28 meters per second squared. What is the frictional force acting on the cart? Again, free body diagram. Always include gravity. normal force and gravity are going to be equal, which is going to be 4.52 times 9.8, which when we do that math, we get an answer of 44.3 newtons. So we know normal force and gravitational force. We got applied force and frictional. Force applied, force of friction. Our applied force is 34.5 newtons, and we're trying to find friction. So net force equals mass times acceleration. Our force applied minus our force of friction equals ma. Our force applied is 34.5 minus our force of friction should equal our mass of 4.52 multiplied by our acceleration of 1.28. We do all this math and we get 5.79 here, and we got 34.5 minus force of friction. So we subtract our 34.5 over, and we get negative force of friction is equal to negative 28.71. Just multiply both sides by negative 1. Our force of friction is 28.71. So for your body diagram, if we're a horizontal, normal force and gravity will be equal. If we're going to be vertical, there's some things you have to think about, and we're going to talk about free fall. So let's say we're in free fall. If there's a string attached, we're going to have a force of tension, but in this case we don't. So if we're in free fall, the only thing acting upon us is the force of gravity, which we know is mass times g, which is 9.8. And if we knew our mass and we knew our force of gravity, we would know our free fall acceleration is going to be 9.8, sometimes rounded to 10. Even if we're a 1 kilogram item, the force of gravity on us in free fall will be 10 newtons, but our acceleration will be the same. Okay. Again, we're negating air resistance. A skydiver jumps out of a helicopter, force of gravity 8.33 newtons in free fall. But as we start to get ourselves situated, we start to develop air resistance. Now, we know that our net force is going to be 833 minus 350. Then it's going to be 833 minus 700, until at some point our force of gravity is counteracted by air resistance. When that happens, acceleration is equal to 0. When acceleration is equal to 0, that means our velocity is constant. And that will happen. Now, when that does happen, we have what is called terminal velocity. And that's where air resistance becomes large enough to balance the force of gravity, to make us move at a constant velocity. And that is the purpose of a parachute. If we can get a parachute to come up and really slow us down, okay, to where even air resistance is greater than gravity, we will start to accelerate downward really, really slow, okay, and we'll hit the ground. But our goal is to get this and this equal so that our acceleration is 0. And when that happens, that constant velocity is that velocity we get when we land. So the force of air resistance becomes large enough to balance the force of gravity. That is the terminal velocity. And you might see some problems where you're going to have gravity, and you might have tension. You might have the force of gravity, and you might have air resistance, right? Or you might just have the force of gravity by itself. Always net force, okay, or our single force, in this case is our net force, equals ma. Have fun solving. If you have any questions, you know where to find me.